Hello. I'd like to talk about projection theorem and orthogonality principle today. Basically, the projection theorem is just refer to the optimum projection of a vector in the Hilbert space onto a subspace C, just like in this diagram in this figure here. Let's say I have this vector x and I have a subspace C. The optimum projection x hat will have the error x minus x hat to be perpendicular to this subspace. In other words, if I have any vector y in this subspace C, I should have x minus x hat to be perpendicular to y, or like x minus x hat, the inner product between x minus x hat and y should be equal to 0. So the proof is very simple. Let's consider any scalar t, and let's say I have x hat deviate from x hat to x hat minus ty, and so something like that. I can imagine this is y, and let's say this is x hat minus ty, and the new error will be something like that, where it will be x minus x hat plus ty. Now, because x hat is optimum, we expect that this new error will be bigger than the original error, so therefore the difference will be bigger than or equal to 0. Now, if we expand this term, of course, the length here is basically just the norm here is just the inner product. So x minus x hat plus ty, and x minus x hat plus ty. So similarly, I have this is actually x minus x hat, x minus x hat. So if I expand that, like basically I have x minus x hat that got cancelled. I have two terms left with something like that. I have t squared y, and I have also like t x minus x hat y, basically x minus x hat ty plus ty x minus x hat. So in general, if I have if I work on a complex space, these two inner products is conjugate of each other, and I will have the sum of them equal to the 2 of the real part of t x minus x hat y. Now, because t is arbitrary, if I pick t to be very small, then the second term can be ignored because the order is much smaller than the first term. And for the first term, because I can change t to be positive or negative, so for this to be always bigger than or equal to 0, I must have this second term here, x minus x hat y is equal to 0, and that gives us the projection theorem. Now, what is the orthogonality principle? It's basically just the projection theorem applied to statistics, or like it's used in signal processing, or like just terminology used in signal processing. So now, if let's say we're trying to estimate some random variable x given some oscillation y, for a linear estimator, I can just write this x hat as just ay. Now I can define the inner product as just the expectation, the inner product between two random variables x and y, just as the expectation between the x and y. Now this inner product will be well defined. You can check that. Basically, it satisfies something like x will be bigger than equal to 0, and it will be equal to 0 only when x is equal to x, and also satisfy associative law like x plus y c is equal to x plus c, x c plus y c, and so on. So because like it satisfies all these properties of inner product, so it's a valid definition for inner product. So therefore, like we can use the projection theorem, which is shown earlier, and so therefore we have the optimum projection, or in other words, the optimum projection refer to the minimum x minus x hat, minimum norm of x minus x hat, right? And that corresponds to the minimum, basically the minimum mean square error, and that will be minimized when we have the projection theorem is satisfied. That's basically x minus x hat is perpendicular to any of the yi, and or in other words, it's just the expectation of x minus x hat yi is equal to 0, or therefore like expectation of x minus x hat, the entire vector, will be equal to 0. So just look at one example here. So we can, let's say now I have, let me use the orthogonality principle to find the optimum AT, the A here. So because of the orthogonality principle, I have this is equal to 0. So therefore I can write that, I can expand that, and I can substitute x hat into that. So I have this, and therefore A transpose is just equal to that. And if I assume everything is 0 mean, then this is just equal to sigma x y sigma y y. I mean, this is equal to sigma xy, and this is equal to sigma yy. And similarly, if I want to find what's the error in that case, the mean square error is just equal to expectation x minus x hat square, but let's see. Because x hat, because x hat is proportional to y, so or maybe I can write like this is equal to expectation x minus x hat x minus A transpose y. Now because this is perpendicular to y here, so the second term is gone. I only have this x minus x hat times x, and if we expand that, we have this here, and expectation x squared is just equal to sigma x squared if we assume that x is 0 mean, and this is expectation x hat x. We can substitute x hat as A transpose y. We have this expectation y x. And A transpose, we got it earlier, is equal to this, so therefore we have this term here. So actually, this is kind of a nice proof for the mean square error, that it applies for any kind of x and y, not just Gaussian x and y. Of course, for Gaussian, we can also show that actually x, even for vector Gaussian, let's say if I have a y a vector y, and we want to estimate a vector x, and we basically project x onto the space of y here. So for like basically x hat is equal to some matrix A multiplied by y. Then we can show that the best linear estimator should be equal to sigma xy, sigma yy inverse y, just like here, and the corresponding covariance is equal to this. So it's kind of like the same form as this one here. Just I have like this sigma xy and sigma xx. Sigma xy here is just a vector actually, really, because x is just it's just a scalar. But here is, so what I mean is like this sigma xy here is actually just equal to sigma xy1, sigma xy2, something like that. But in this case, I have the x is a vector, so I have like in this case I have sigma xy is like, maybe I put a to just emphasize that, equal to sigma x1, sigma y1, sigma x2, sigma y2, and so on. I have a sigma x2, sigma y1, and blah blah blah, something like that. And of course, again, like I want to emphasize this equation holds when I have zero mean. When x and y are not zero mean, then this is basically still the same if this is the covariance, as long as this is the covariance, and this in that case, of course, this sigma is still equal to this guy here. I want to say, wait a sec. Actually, I didn't write it correctly. Should be sigma x1 y1, sigma x2 y2, something like that. So when it's zero mean, this is just expectation x1 y1, something like that. So if it's not zero mean, this should be equal to expectation x1 minus x1 bar, y1 minus y1 bar. So where this x1 bar is the mean of x1. But the covariance is still the same. The conditional covariance is still the same, but the mean here, basically the optimum estimator here, will become different. We just need to adjust the mean, basically. So it will be something like we need to first subtract the mean for the observation, and for the estimate we want to add back the mean, so something like that. Okay, I guess that's all. This is a short video, not so short, I guess, for a projection theorem and orthogonality principle. I hope that it was not too confusing.